Hello there, and welcome to Cosmos for Sleep. Tonight, we're embarking on a serene journey through the fascinating realm of exoplanets, discovering the many worlds that drift far beyond our solar system. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe. Let your eyes grow heavy. And let's begin. Astronomers now believe that most stars in our galaxy likely host at least one planet. For centuries, our solar system seemed to be a unique cosmic arrangement. But Hello there, and welcome to Cosmos for Sleep. Tonight, we're embarking on a serene journey through the fascinating realm of exoplanets, discovering the many worlds that drift far beyond our solar system. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe. Let your eyes grow heavy. And let's begin. Astronomers now believe that most stars in our galaxy likely host at least one planet. For centuries, our solar system seemed to be a unique cosmic arrangement, but modern observations have gently unveiled a universe teeming with countless other worlds. This quiet understanding suggests that planets are not rare celestial occurrences, but rather a common, almost universal feature of stars. Imagine the vastness of the Milky Way, with its hundreds of billions of stars, and then consider that the majority of these luminous points of light could be cradling their own families of planets. This pervasive presence of planetary systems hints at an astonishing cosmic abundance, a tranquil tapestry woven with countless worlds. Extending this profound insight, scientists estimate that billions of exoplanets may exist within the Milky Way galaxy alone. This staggering number invites contemplation, as each of these countless worlds represents a unique cosmic canvas, potentially offering diverse landscapes, atmospheres, and histories. While our current count of confirmed exoplanets is over 5,000, this is merely a whisper compared to the estimated total. The sheer volume of these silent wanderers, each patiently tracing its orbital path around its parent star, is a multitude far exceeding the grains of sand on all Earth's beaches. This quiet census of celestial bodies speaks to the profound richness of our galactic home, suggesting an almost infinite variety of planetary experiences awaiting discovery. The universe, in its serene generosity, has populated its stellar nurseries with an unimaginable array of worlds, each a testament to the elegant processes of cosmic formation. Amidst these ordered planetary systems, another intriguing class of worlds exists. Rogue planets that drift through interstellar space without orbiting a star. These solitary wanderers are not bound by the gravitational embrace of any sun, instead, embarking on an endless, silent journey through the cosmic void. Scientists believe these planets may have been gently ejected from their nascent star systems during chaotic early formation, perhaps receiving a gravitational nudge from a passing giant planet or a nearby star. Alternatively, some might have formed in isolation, never finding a star to call their own, instead condensing directly from clouds of gas and dust in the deep interstellar medium. Their existence highlights the dynamic and sometimes unpredictable nature of cosmic evolution, offering a glimpse into worlds that experience perpetual twilight, illuminated only by the faint, distant glow of galaxies, their surfaces likely frozen to extreme temperatures. These free-floating spheres represent a unique form of planetary life, moving with quiet purpose through the vast, cold expanse between the stars. In stark contrast to these unbound wanderers, some exoplanets reside in orbits so extraordinarily close to their parent stars that their years last only a few hours. These worlds complete an entire revolution around their star in a span of time briefer than an Earth day, experiencing a rapid succession of orbital cycles. Imagine a planet where sunrise and sunset occur within a single afternoon, a world where the passage of time is dramatically accelerated by its intimate stellar embrace. On such worlds, the close proximity to their star generates immense tidal forces, often tidally locking them so that one side perpetually faces their sun. This constant exposure to intense stellar radiation shapes their atmospheres and surfaces in unique ways, creating landscapes that are dramatically different from anything found in our own solar system. Such fleeting years offer a glimpse into the diverse temporal rhythms that govern planetary existence across the cosmos, where the celestial clock ticks at a vastly different pace. Further pushing the boundaries of planetary extremes, some exoplanets are so incredibly hot that their surface temperatures exceed those of many stars. These ultra-hot worlds, often gas giants or terrestrial planets orbiting exceptionally close to their suns, are bathed in such intense stellar radiation that their outer layers can reach thousands of degrees. For instance, some of these worlds have measured temperatures exceeding 4,000 degrees Fahrenheit, a heat so profound it would vaporize most known materials. This extreme heat can cause their atmospheres to swell dramatically, turning them into puffy, extended envelopes of gas, or even slowly evaporate into space, creating extended gaseous tails, much like a comet. The very notion of a planet being hotter than a cool star challenges our conventional understanding, revealing a universe where the boundaries between different celestial bodies can blur under the influence of immense energy. These fiery worlds are a testament to the powerful interactions between stars and their closest planetary companions, showcasing the raw, unbridled power of stellar proximity. The journey of exoplanet discovery began in a most unexpected place. The very first exoplanet ever confirmed was found orbiting a rapidly spinning neutron star known as a pulsar. This groundbreaking discovery in the early 1990s challenged prevailing notions of where planets could form and survive. Pulsars are the incredibly dense, compact remnants of massive stars that have undergone a final burst of radiance, leaving behind a core that spins with astonishing speed, emitting precise beams of radiation. The planet PSR B1257+12b, for example, orbits a pulsar, experiencing a stark and silent environment. The presence of planets around such a stellar corpse suggested that planetary formation, or perhaps reformation from the debris of the star's dramatic demise, could occur even in the aftermath of a supernova. It was a gentle reminder that the cosmos often holds surprises, extending the potential for worlds to exist in the most unlikely of stellar neighborhoods, prompting astronomers to broaden their search beyond sun-like stars. The cosmic ballet of planets can also involve more than one central star. Indeed, planets can orbit two suns, a celestial arrangement that brings to mind the iconic imagery of a fictional desert world. These circumbinary planets experience the gentle yet complex gravitational pull of two stellar companions, tracing intricate paths around their dual centers of gravity. Imagine standing on such a world, witnessing two suns gracefully traverse the sky, offering a double sunset and sunrise, painting the landscape with shifting patterns of light and shadow, creating a dynamic and ever-changing sky. The gravitational dynamics in these systems are complex, requiring a delicate balance to maintain stable orbits. Yet they demonstrate the universe's capacity to create stable planetary homes even amidst the elegant dance of binary stars. These dual star systems offer a serene perspective on the varied architecture of planetary orbits, where cosmic companionship can take many forms, leading to unique and mesmerizing celestial displays. Beyond the gentle ballet of binary stars, the universe holds worlds of truly astonishing and extreme conditions. Imagine a planet where the very air shimmers with metallic vapor, leading to a phenomenon almost beyond terrestrial comprehension. On some exoplanets, scientists believe that superheated iron may literally rain from the sky. These distant worlds, often orbiting exceptionally close to their parent stars, are subjected to such intense heat that heavy metals like iron can vaporize in their atmospheres. As these metallic vapors rise to cooler altitudes or drift towards a planet's shadowed night side, they condense into liquid droplets. Gravity then gently pulls these molten metal drops downward, creating a surreal and beautiful precipitation of liquid iron. This extraordinary weather system paints a picture of a truly alien environment, where the familiar cycle of rain is transformed into a majestic cascade of liquid metal, a silent, glittering descent unlike any storm known on Earth. Such worlds remind us of the universe's capacity for unexpected and profound atmospheric phenomena. The constant ebb and flow of this metallic rain would sculpt the landscape in ways we can only imagine, creating formations of solidified iron under a sky that endlessly cycles between vapor and liquid metal. It is a tranquil yet powerful illustration of how stellar proximity can reshape planetary chemistry and meteorology, forging landscapes of metallic rivers and mountains under a sky that weeps liquid ore. Continuing this exploration of extreme planetary compositions, some theoretical models suggest that certain planets might even possess oceans of liquid diamonds. This captivating idea arises from the unique conditions found on worlds rich in carbon, particularly those experiencing immense internal pressure and high temperatures. Deep within the mantle of such a planet, where carbon is abundant and pressures are hundreds of thousands of times greater than those on Earth, the element could transform into its crystalline diamond form. Furthermore, under specific temperature and pressure regimes, scientists theorize that these diamonds could melt, forming vast shimmering seas of liquid carbon. Picture expansive, placid oceans, not of water, but of pure molten diamond, reflecting the distant starlight with an unimaginable brilliance. Such a discovery would redefine our understanding of planetary geology and the potential for exotic material states within celestial bodies. These deep, luminous oceans would represent a silent, shimmering testament to the profound forces at play in the heart of distant worlds, where matter itself takes on forms of breathtaking beauty and rarity. The gentle currents within these theoretical diamond seas would flow with an unhurried grace, holding secrets of creation forged under unimaginable cosmic weight. Shifting our gaze to atmospheric phenomena, other worlds could present an even more unusual spectacle: skies that rain glass sideways in fierce winds. Consider the exoplanet HD 189,733b, a gas giant with a deep blue hue. Observations suggest that its atmosphere contains silicate particles, the very building blocks of glass. Combined with temperatures soaring to nearly 2,000 degrees Fahrenheit and winds estimated to rage at over 4,000 miles per hour, these conditions create an astonishing meteorological display. The superheated silicate particles would condense into tiny, sharp shards of glass, which are then propelled horizontally by the planet's ferocious winds. Imagine a constant, imperceptible deluge of sharp glass driven across the planet's face at supersonic speeds, creating an environment utterly inimical to life as we know it. This dramatic weather pattern underscores the incredible diversity of atmospheric dynamics beyond our solar system, where familiar substances behave in entirely unfamiliar ways, carried by the relentless breath of a distant star. The silent, almost delicate scything of these glass particles across the sky paints a vivid picture of a world sculpted by an elegant, yet unforgiving, cosmic gale. Among the fascinating classifications of exoplanets are Chthonian planets, which are thought to be the stripped cores of gas giants. The term Chthonian derives from ancient Greek, referring to the underworld, aptly describing these remnants. Scientists believe that these dense terrestrial worlds began their lives as much larger gas giants, similar in size to Jupiter or Neptune. However, due to their extremely close proximity to their parent star, the intense stellar radiation and powerful stellar winds gradually eroded and stripped away their thick gaseous envelopes over billions of years. What remains is the planet's original, heavy core, a dense, rocky or metallic sphere that once lay hidden beneath layers of hydrogen and helium. These Chthonian planets represent a cosmic transformation, a slow, gentle unveiling of a planet's innermost essence, revealing the enduring legacy of a gas giant's past. Their existence provides valuable insights into the long-term evolution of planetary systems and the powerful, shaping influence of a star on its closest companions, leaving behind a silent monument to a lost atmosphere. In a remarkable contrast to the density of Chthonian worlds, Some exoplanets have been discovered that defy conventional expectations of planetary mass and size. These intriguing objects are known as superpuffs, a name that perfectly describes their unusually low density. Despite being comparable in size to Jupiter, the largest planet in our solar system, these superpuffs possess masses that are only a few times that of Earth. This means they are incredibly light for their immense volume. With densities so low, they are often compared to cotton candy, or even styrofoam. Their enormous size, coupled with their minuscule mass, suggests they have extremely extended and diffuse atmospheres, perhaps hundreds of miles deep, making them appear far larger than their solid cores would suggest. The formation and composition of these airy giants remain an area of quiet scientific inquiry, hinting at unique atmospheric processes or formation scenarios that allow such vast yet ethereal structures to exist. These gentle giants float through their stellar systems, a serene enigma in the cosmic tapestry, their lightness a testament to the universe's varied forms of planetary existence. Many exoplanets, especially those orbiting close to their stars, experience a phenomenon known as tidal locking. This means that one side of the planet perpetually faces its star, while the other remains in eternal darkness. The strong gravitational pull of the parent star causes the planet's rotation to slow down over eons until the same hemisphere is always illuminated, creating a world of stark and unwavering contrast. On the perpetually sunlit side, temperatures would soar, potentially leading to vast, dry deserts or even molten surfaces. Conversely, the eternally dark side would be plunged into a deep, frigid cold, where ice and desolation might reign. Between these two extremes lies a narrow terminator zone, a band of perpetual twilight where conditions might be more temperate, perhaps even stable enough for liquid water to exist. This gentle, yet relentless, gravitational embrace creates planets of profound duality, where the passage of day and night is replaced by an unchanging cosmic tableau, a silent testament to the star's dominant influence. Among the most commonly detected types of exoplanets are hot Jupiters. These are massive gas giants, similar in size and composition to Jupiter, but with a crucial difference: they orbit incredibly close to their parent stars. Their orbital periods are often measured in mere days or even hours, placing them far inside the orbit of Mercury in our own solar system. This extreme proximity means they are subjected to intense stellar radiation, heating their atmospheres to scorching temperatures. As a result, many hot Jupiters are observed to have expanded, puffed up atmospheres due to this intense heat. Their discovery profoundly challenged early theories of planetary formation, which predicted that gas giants should only form in the cooler, outer regions of a star system. Scientists now believe that many hot Jupiters formed further out and then migrated inward over billions of years, a slow and patient journey guided by gravitational interactions within their nascent systems. These close-orbiting giants are a serene puzzle, revealing the dynamic and evolving nature of planetary architecture, and reminding us that our solar system's arrangement is just one of many tranquil possibilities in the vast cosmos. Their majestic, yet unhurried migration paths speak to the subtle gravitational forces that sculpt worlds into their final captivating forms, can choreograph even grander celestial ballets. Astronomers have remarkably discovered planets that have been found orbiting 4 stars, all engaged in a complex and intricate gravitational dance. Imagine a world where the sky is graced by not just 1 or 2, but 4 distinct sources of light, each casting its own unique glow and shadow across the landscape. The gravitational influences in such a quad-star system are extraordinarily intricate, creating a delicate balance that allows planets to maintain stable, long-term orbits. These systems are a testament to the universe's capacity for complex celestial architecture, where worlds patiently trace their paths under a multitude of suns. The interplay of light and warmth from 4 different stars would create a constantly shifting tapestry of illumination, a truly unique experience for any celestial observer. Each star, with its own color and intensity, would contribute to a dynamic and ever-changing sky, offering a panorama of multiple sunrises and sunsets, a serene spectacle unfolding over eons. Such a planetary abode would be a rare gem, a world where the cosmic embrace of not one, but four stellar parents guides its gentle journey through space. The stability required for a planet to exist in such a system speaks volumes about the enduring nature of gravity's influence. Holding these diverse components in a harmonious yet complex celestial design, it is a quiet wonder, demonstrating how deeply intertwined the fates of stars and planets can become, even when many stellar bodies are involved, each contributing to a rich, luminous environment. Expanding our view across the vast cosmic timeline, we find that exoplanets orbit stars much older than our Sun, with some systems nearly as old as the universe itself. Our own Sun is a relatively middle-aged star, at about 4.5 billion years old. Yet astronomers have uncovered planets circling stars that are 10, 11, or even 12 billion years old. These ancient worlds have patiently endured for eons, witnessing the slow, unhurried unfolding of cosmic history. Their existence suggests that planetary formation began very early in the universe's story, shortly after the first stars enriched the cosmos with the heavier elements necessary to build rocky worlds. These venerable exoplanets, some of which may have existed for twice as long as Earth, offer a profound sense of continuity, silently orbiting their aged suns, having outlived countless generations of other celestial phenomena. They are quiet testaments to the enduring nature of planetary systems, persisting through billions of years of cosmic change, their surfaces and atmospheres carrying the silent imprints of an immensely long and tranquil past. The sheer longevity of these systems speaks to a deep, underlying stability within the universe, where worlds can thrive for vast stretches of cosmic time. The gentle cycle of stellar life and death also influences where planets can be found. In a remarkable twist, planets can orbit white dwarfs, the dense remnants of dead stars. A white dwarf is what remains of a star like our Sun after it has exhausted its nuclear fuel, gently shedding its outer layers to expose a compact, incredibly dense core. These stellar corpses are typically Earth-sized, but contain the mass of a sun, slowly cooling over billions of years. The discovery of planets orbiting these faint, slowly fading embers suggests that some worlds can gracefully survive the dramatic final stages of their parent star's life. While the star's expansion into a red giant would have engulfed and destroyed any inner planets, those further out could have endured, continuing their quiet orbits around the star's shrunken, dense core. These resilient planets are silent witnesses to a stellar transformation, now bathed in the subdued, fading light of a star that once shone brightly. Their presence offers a tranquil glimpse into the universe's capacity for planetary survival, even in the face of immense stellar change, continuing their cosmic journey around a star's serene, enduring legacy. Not all stellar objects manage to ignite into full-fledged stars. Some planets orbit brown dwarfs, which are often referred to as failed stars, because they are too small to sustain the nuclear fusion reactions that power true stars. Brown dwarfs are larger than gas giant planets, but smaller than the smallest stars, emitting only a faint, reddish glow from their residual heat. Planets orbiting these dim, cool objects would exist in a perpetual cosmic twilight, receiving far less light and warmth than those orbiting sun-like stars. This creates an environment of subdued illumination, where the distant brown dwarf appears as a dull, ruddy orb in the sky. Despite the low energy output of their parent body, these systems demonstrate that planetary formation is not exclusive to bright, active stars. The existence of planets around brown dwarfs further expands our understanding of the diverse conditions under which worlds can coalesce and thrive, even in the quiet, cool embrace of a celestial body that never quite achieved stellar brilliance. Their gentle presence reminds us that the definition of a star system is far broader and more varied than once imagined. Indeed, the concept of a single sun in a planetary system, as we have in our own solar system, is not necessarily the cosmic norm. Many exoplanets reside in multi-star systems, experiencing multiple sunrises and sunsets as they gracefully orbit their stellar companions. These celestial arrangements, where 2, 3, or even more stars share a gravitational bond, offer a truly mesmerizing spectacle. Imagine a world where the sky is painted with the shifting hues of 2 or 3 different suns, each rising and setting at its own pace, creating a dynamic interplay of light and shadow throughout the day. The colors of the stars themselves, ranging from fiery red to brilliant blue, would create a constantly evolving palette across the planetary landscape. This commonality of multi-star systems profoundly expands our imaginative scope of what a day might entail on another world, where the celestial choreography is a complex and beautiful dance of multiple luminous bodies. These worlds offer a tranquil yet vibrant illustration of the diverse ways in which light can grace a planet, providing varied patterns of illumination across its surface, a testament to the elegant gravitational ballet of multiple stellar companions. Bringing our focus closer to home, the Proxima Centauri system, our closest stellar neighbor, hosts at least 2 planets. Proxima Centauri is a small, cool red dwarf star located just over 4 light-years away. Its gentle, reddish glow is far dimmer than our Sun's, yet it harbors at least 2 confirmed exoplanets, Proxima Centauri b and Proxima Centauri c. Proxima Centauri b is particularly intriguing, as it orbits within the star's habitable zone, the region where conditions might allow for liquid water to exist on its surface. While the star is prone to flares, its close proximity makes it an ideal candidate for further study and potential future exploration. The discovery of planets in this system, so close to us, serves as a gentle reminder that planetary companionship is not just a distant phenomenon, but a reality unfolding in our immediate cosmic neighborhood. These nearby worlds offer a tangible connection to the broader exoplanet census, inviting us to contemplate the quiet possibility of life existing just a gentle cosmic stone's throw away, under the soft, enduring gaze of a nearby red dwarf star. The silent vigil of these planets around our closest star fuels our curiosity about the myriad worlds that populate our galactic vicinity. The discovery of these nearby worlds, coupled with the vast number of exoplanets detected across the galaxy, underscores the principle that the universe is a place of profound planetary abundance. We are not merely isolated inhabitants of a single star system, but rather part of a much larger, intricate tapestry of worlds. Each new discovery, from planets orbiting 4 stars to those enduring around ancient stellar remnants, gently expands our understanding of where planets can form and what forms they can take. These findings suggest that the conditions for planetary existence are far more varied and robust than once imagined, hinting at a cosmos generously populated with silent orbiting spheres. The quiet prevalence of these diverse worlds invites us to ponder the countless forms that planetary life can assume, from the superheated to the deeply frozen, from the dense cores of stripped giants to the airy expanses of superpuffs. It is a tranquil revelation, affirming that the universe, in its boundless elegance, is a realm of endless planetary possibilities, each world a unique note in a silent, cosmic symphony. Our continuing journey through the quiet wonders of the cosmos now leads us to the heart of the search for life beyond Earth, beginning with the serene concept of the habitable zone. This crucial region around any given star is defined as the range of distances where a planet's surface temperature could gently allow for the stable presence of liquid water. Liquid water, as scientists understand it, is an indispensable ingredient for life, acting as a universal solvent for chemical reactions and a vital medium for biological processes to unfold. This zone is often referred to with a gentle analogy as the Goldilocks zone, signifying conditions that are just right, neither too warm, which would cause water to evaporate into space, nor too cold, where it would remain perpetually frozen in solid ice. The precise location and width of this delicate band of habitability are not fixed, They gracefully shift depending on the specific characteristics of the parent star. A hotter, more luminous star, for instance, would project its habitable zone further into its system, while a cooler, dimmer star, such as a red dwarf, would host its habitable zone much closer to its gentle glow. It is within these cosmic sweet spots that astronomers serenely focus their efforts, patiently seeking out worlds that might offer the fundamental conditions for life's delicate emergence and its sustained, tranquil existence. The stable presence of liquid water, whether gathered in vast oceans, tranquil lakes, or hidden underground reservoirs, offers a fundamental, nurturing foundation for biological processes to slowly evolve over immense stretches of cosmic time. This essential requirement guides our serene exploration of distant planetary shores, providing a crucial filter in the boundless sea of exoplanet discoveries, leading us to contemplate the subtle balance required for life to flourish. One of the most remarkable discoveries in this tranquil quest for habitable worlds is the TRAPPIST-1 system, which hosts 3 Earth-sized planets quietly orbiting a small, cool star, all residing within its potentially habitable zone. This extraordinary system, located about 40 light-years away, revolves around an ultra-cool red dwarf, a star significantly smaller and dimmer than our Sun. Despite its modest luminosity, this star maintains a compact gravitational embrace, allowing 7 planets, all roughly Earth-sized, to orbit closely. Of these 7, 3 are particularly compelling candidates for habitability, positioned so that liquid water could theoretically exist on their surfaces. Due to their close proximity to their parent star, these planets are likely tidally locked, meaning one side perpetually faces their sun in eternal daylight, while the other remains in endless night. This creates a fascinating balance, where a narrow band of perpetual twilight, known as the Terminator line, might offer the most stable conditions for life. The TRAPPIST-1 system is a profound example of how small, long-lived stars can foster an intimate family of worlds, creating a quiet cosmic neighborhood ripe for further exploration and serene contemplation. The possibility of 3 potentially habitable worlds in such close celestial proximity is a testament to the universe's abundant capacity for planetary formation, offering a tranquil glimpse into the diverse cradles of potential life. As we expand our understanding of planetary forms, we encounter super-Earths, a common type of exoplanet that is larger than Earth but smaller than Neptune, yet has no direct equivalent within our own solar system. These intriguing worlds typically range in mass from about 1 to 10 times that of Earth, and in radius from 1 to 2 times. Their prevalence in the galaxy suggests that planetary formation processes frequently lead to worlds of this intermediate size, a scale that our solar system simply skipped. Super-Earths could be diverse in their composition. Some might be predominantly rocky, possessing deep, rich mantles and cores, while others could be ocean worlds with vast liquid surfaces, or even possess substantial gaseous envelopes, blurring the line with mini-Neptunes. Their larger mass often means they possess stronger gravity, which could potentially aid in retaining a thicker atmosphere, a factor that might enhance their habitability. However, the exact nature of their surfaces and atmospheres remains a gentle area of ongoing scientific inquiry. These ubiquitous mid-sized planets represent a significant portion of the exoplanet population, quietly inviting astronomers to explore an entirely new class of planetary environments, each a unique expression of cosmic geology and atmospheric science. Their silent presence fills a fascinating gap in our cosmic understanding. Closely related to super-Earths are mini-Neptunes, another exceptionally common exoplanet type that is also larger than Earth but smaller than Neptune, characterized by their thick, hydrogen-rich atmospheres. Unlike rocky super-Earths that might have thin atmospheres, mini-Neptunes possess substantial envelopes of gas that make them appear larger and less dense than their rocky counterparts. These planets are thought to consist of a small, rocky core surrounded by a deep, dense layer of water, ammonia, or methane, encased in a vast atmosphere of hydrogen and helium. While they are abundant across the galaxy, Their thick, high-pressure atmospheres generally render them unsuitable for surface life as we know it. The immense pressures and soaring temperatures found deep within their gaseous layers would be inhospitable to organic chemistry, making the existence of liquid water on a solid surface unlikely. However, their study is crucial for understanding planetary formation and evolution, as they represent a common outcome of the processes that sculpt worlds around distant stars. Mini-Neptunes offer a tranquil window into alternative pathways of planetary development, showcasing how a planet's initial gas accretion can lead to a vast, gaseous shroud rather than a solid, temperate surface. Their silent, ethereal forms drift through the cosmos, a testament to the diverse ways in which planetary matter can coalesce. The quest for life beyond our home planet also involves the meticulous study of biosignatures, which are chemical clues in the atmospheres of exoplanets that might indicate the presence of life. Scientists carefully analyze the light from distant stars as it passes through an exoplanet's atmosphere, searching for specific molecular absorption lines. The detection of certain gases, such as oxygen, methane, ozone, or specific combinations of these, in concentrations that cannot be easily explained by non-biological processes, could serve as a potential biosignature. For instance, the simultaneous presence of oxygen and methane in significant quantities is a strong indicator, as these gases tend to react with each other and require constant replenishment, a process often attributed to living organisms. While a single biosignature is not definitive proof of life, the careful observation of multiple corroborating clues would gently strengthen the case. Telescopes like the James Webb Space Telescope are now capable of such delicate atmospheric analysis, offering unprecedented opportunities to probe the chemical compositions of these distant worlds. The serene pursuit of these atmospheric whispers represents humanity's patient listening for any distant echoes of life across the vast cosmic ocean, a quiet hope for cosmic companionship. Finally, the concept of ocean worlds suggests planets entirely covered in deep liquid water, an idea that profoundly reshapes our vision of habitable environments. These worlds are not merely terrestrial planets with oceans, but rather spheres where water, in its liquid and sometimes exotic ice forms, dominates the entire planetary body. Imagine a planet without any landmasses, only a boundless, tranquil sea stretching across its entire surface, potentially hundreds or even thousands of miles deep. Beneath these vast liquid layers, extreme pressures could compress water into exotic forms of ice, such as Ice 7, which is denser than liquid water and would form the planet's mantle around a rocky core. On such worlds, life might not reside on a surface, but rather in the deep, dark depths, potentially thriving around hydrothermal vents on the seafloor, much like some ecosystems found in Earth's own deep oceans. Scientists believe that such ocean worlds could be more common than planets with distinct landmasses like Earth, increasing the potential for life to emerge in the universe. These serene, water-laden spheres offer a tranquil vision of life's adaptability, suggesting that the cosmos might be teeming with deep-sea biospheres, patiently evolving in worlds defined by their profound liquid embrace, a testament to water's ubiquitous role in cosmic biology. Cosmos, inviting us to delve deeper into their secrets by patiently studying the very air they breathe. One of the most profound avenues of exoplanet exploration involves peering into the delicate veils that shroud these distant worlds. Astronomers can gently analyze the atmospheres of exoplanets by studying starlight passing through them, a technique known as transit spectroscopy. When a planet gracefully glides in front of its host star from our perspective, a tiny fraction of the star's light filters through the planet's atmosphere before reaching our telescopes. As this light traverses the atmospheric gases, certain wavelengths are absorbed, leaving subtle, yet distinct, chemical fingerprints. Each element and molecule in the atmosphere has a unique spectral signature, like a cosmic barcode. By meticulously decoding these faint signals, scientists can determine the composition of the exoplanet's atmosphere, revealing the presence of water vapor, methane, carbon dioxide, and other compounds. This gentle art of stellar eavesdropping allows us to learn about the temperature, pressure, and chemical makeup of these alien skies, providing an intimate glimpse into worlds light years away. It is a tranquil and sophisticated method, allowing us to perceive the invisible breath of distant planets, patiently collecting data that speaks volumes about their nature and potential. The subtle dance of light through alien air unveils profound truths about these distant spheres, offering a quiet communion with their atmospheric essence. Through these delicate observations, water vapor has indeed been detected in the atmospheres of many exoplanets, a discovery that often brings a sense of quiet wonder. The presence of water, even in gaseous form, is a significant finding because it is an essential ingredient for life as we understand it. Its detection suggests that the building blocks for life are not uncommon in the universe, and that water, a familiar and nurturing substance on Earth, is also a widespread component of distant planetary systems. While water vapor in a scorching hot atmosphere might not immediately imply liquid oceans, it confirms that water was likely incorporated into the planet during its formation or delivered later by comets. These detections are often made on gas giants or hot Jupiters, where the water remains gaseous due to extreme temperatures. However, observing water vapor on smaller, cooler worlds within the habitable zone is an even more thrilling prospect, gently hinting at the possibility of liquid water clouds or even oceans. Each detection of this precious molecule is a soft whisper from the cosmos, suggesting that the conditions for life might be more prevalent than once imagined, painting a serene picture of a universe potentially rich with this life-giving compound. However, not all atmospheric views are clear. Some exoplanets have thick, hazy atmospheres that gently obscure their surfaces, presenting a veil of mystery to our distant observations. These hazes are often composed of tiny particles, sometimes complex organic molecules, or even silicate dust, formed by photochemical reactions in the upper atmosphere. Similar to the thick orange haze that perpetually shrouds Venus in our own solar system, these atmospheric blankets can block out visible light, making it challenging to directly observe the planet's surface or even penetrate deeply into its lower atmosphere. For astronomers, these hazy worlds represent a serene puzzle. While the haze itself can offer clues about the planet's chemistry and atmospheric processes, it also conceals the potential secrets of the world beneath. It hints at powerful atmospheric dynamics and chemical pathways that create these opaque layers, shaping the planet's climate and surface conditions in profound ways. These veiled worlds drift through space, their true nature hidden behind a soft, persistent atmospheric curtain, patiently awaiting more advanced observational techniques to gently part their hazy skies and reveal what lies beneath. The tranquil mystery of these shrouded planets adds another layer to the diverse tapestry of exoplanetary environments. Adding to the diversity of these distant skies, exoplanet atmospheres can contain exotic chemicals not found in abundance on Earth, such as titanium oxide. These unusual compounds are typically detected in the atmospheres of extremely hot exoplanets, where temperatures are high enough to keep refractory materials, which are normally solid or liquid on cooler worlds, in a gaseous state. Titanium oxide, for example, is a strong absorber of visible light and can play a significant role in the heat balance and cloud formation on ultra-hot Jupiters. Its presence offers valuable insights into the extreme chemical processes occurring in these fiery atmospheres, revealing a chemistry far removed from our terrestrial experience. Imagine atmospheric layers where metallic compounds float as gases, absorbing and scattering starlight in ways that create unique atmospheric profiles. These exotic chemical detections gently expand our understanding of the universe's chemical palette, demonstrating that the elements present in a planet's atmosphere can combine in unexpected ways under extreme conditions, creating a truly alien atmospheric brew. The silent spectral lines of these unusual molecules speak of worlds where the very air is woven from materials alien to our everyday experience, a serene testament to cosmic alchemy. The most exciting atmospheric discoveries often revolve around the search for biosignatures, where the presence of methane or oxygen in an exoplanet's atmosphere could be a compelling chemical clue that might indicate life. On Earth, the vast majority of oxygen in our atmosphere is produced by photosynthesis, a biological process. Similarly, methane can be produced by geological processes, but its presence alongside oxygen in significant quantities or in concentrations that are out of equilibrium with the surrounding environment would be highly suggestive of biological activity. Life, in its gentle persistence, often creates imbalances in atmospheric chemistry that would otherwise naturally dissipate. The detection of such a chemical disequilibrium would serve as a powerful yet subtle hint that biological processes are actively altering the planet's atmospheric composition. Scientists are meticulously developing sophisticated models to distinguish between biological and non-biological sources of these gases, understanding that a single detection is not definitive. Rather, it is the patient accumulation of multiple lines of evidence, a chorus of chemical whispers that might eventually point to the tranquil presence of life on a distant world. This serene quest for the chemical breath of life is a testament to humanity's enduring hope for cosmic companionship. However, a planet's atmosphere is not a static shield. It can be a dynamic, evolving entity. Atmospheric escape is a process where a planet's atmosphere is gradually stripped away by its star's radiation and stellar winds, a slow and patient erosion over immense spans of time. Planets orbiting very close to their parent stars, especially active stars like red dwarfs that frequently unleash powerful flares, are particularly vulnerable to this gentle yet relentless stripping. The high-energy radiation and charged particles from the star can heat the upper layers of the planet's atmosphere, causing gas molecules to gain enough energy to escape the planet's gravitational pull and drift away into space. This process can transform a once gaseous world into a dense, rocky core, potentially leading to the formation of a Chthonian planet. Atmospheric escape is a subtle, ongoing cosmic phenomenon that profoundly influences a planet's long-term habitability and evolution. It highlights the delicate balance between a star's energetic output and a planet's ability to retain its life-sustaining atmospheric envelope, reminding us that planetary conditions are in a constant, unhurried state of flux under the gentle yet powerful influence of their stellar parent. The silent departure of atmospheric gases is a slow, elegant dance of cosmic transformation. This graceful cosmic ballet of atmospheric transformation leads us to consider the very origins of these distant worlds, as planetary systems are believed to form from rotating disks of gas and dust around young stars. Imagine a nascent star, freshly ignited, still surrounded by a vast, flattened swirl of primordial material, a protoplanetary disk. This tranquil disk, composed of countless microscopic particles of dust, ice, and gas, slowly spins, resembling a colossal, ethereal cosmic frisbee. Within this gentle, swirling expanse, gravity begins its patient work, causing dust grains to gently collide and stick together, gradually forming larger and larger clumps. Over millions of years, these small aggregates accrete more material, growing into pebbles, then boulders, and eventually into planetesimals. These planetesimals continue their slow, unhurried collisions and mergers, gradually sweeping up material from their orbital paths, giving birth to the serene, spherical forms of planets. This elegant process of accretion, driven by the subtle yet persistent force of gravity, sculpts the raw material of the cosmos into organized, harmonious systems of orbiting worlds. It is a quiet, majestic dance of creation, where the universe patiently forms new homes from stellar nurseries, each a testament to the fundamental forces at play in the birth of celestial bodies. Once formed, planets do not always remain in their original orbital positions. The concept of planetary migration gently suggests that planets can indeed move from their birth orbits to new positions within their stellar systems. This unhurried shift is often driven by subtle gravitational interactions between the nascent planet and the surrounding gas and dust disk. or later, by gravitational nudges from other massive planets within the system. As a planet interacts with the material in the disk, it can either lose or gain orbital energy, causing it to drift either inward towards its star or outward into cooler, more distant regions. This migration is typically a slow, gradual process, unfolding over millions of years, a patient cosmic journey rather than a swift relocation. The idea of planetary migration profoundly reshapes our understanding of how solar systems evolve, suggesting that the current architecture of a planetary system may not be the same as its initial configuration. It paints a picture of dynamic, evolving systems where planets are not static, but rather gracefully wander through their stellar neighborhoods, seeking their final, stable resting places. This tranquil repositioning is a key factor in explaining the diverse arrangements of exoplanetary systems we observe today. Indeed, observations confirm that some exoplanets formed in the outer, cooler regions of their systems, and then migrated inward towards their parent stars. This gentle inward journey is particularly important for understanding the prevalence of certain types of planets, such as the hot Jupiters. These gas giants, which we have discussed before, are found incredibly close to their stars, a location where it was once thought impossible for such massive planets to form due to the intense heat. The migration hypothesis provides a serene explanation. These planets likely coalesced in the colder outer reaches of their protoplanetary disks, where abundant ice and gas allowed them to grow to immense sizes. Once fully formed, their gravitational interactions with the remaining disk material or other planets caused them to slowly spiral inward, eventually settling into their tight, close orbits. This unhurried inward drift is a testament to the powerful, yet subtle, gravitational forces that can reshape an entire planetary system over vast timescales. It reveals a cosmos where planets are not fixed in their initial locations, but embark on long, graceful journeys, profoundly influencing the final appearance and dynamics of their stellar families. The discovery of the hot Jupiter phenomenon, as noted earlier, significantly challenged older planet formation theories. Prior to their detection, the prevailing models, largely based on our own solar system, predicted that massive gas giants would only form in the cold, outer regions of a star system, far from the intense heat of the central star. The logic was that rocky planets, composed of heavier elements, would form closer in, while lighter gases and ices would condense further out. However, the prevalence of hot Jupiters, immense gas giants orbiting astonishingly close to their stars, presented a serene puzzle. Their existence demanded a re-evaluation of these long-held assumptions. This gentle intellectual challenge led astronomers to develop new theories, such as planetary migration, to account for these unexpected worlds. The hot Jupiter phenomenon thus became a cornerstone of modern exoplanetology, gracefully pushing the boundaries of our understanding and revealing a universe far more diverse and dynamic in its planetary architectures than previously imagined. It was a quiet revolution in our understanding of cosmic formation, opening our minds to a wider array of planetary possibilities. A crucial concept in understanding where different types of planets form within a protoplanetary disk is the snowline. This imaginary boundary in a protoplanetary disk marks the distance from the central star, where volatile compounds such as water, methane, and ammonia are cold enough to condense from gas into solid ice. Closer to the star, temperatures are too high, and these compounds remain in a gaseous state. Beyond the snowline, however, the temperature drops sufficiently, allowing these icy materials to become solid. This distinction is profoundly important because ice provides a much greater reservoir of solid material for planets to accrete. Therefore, regions beyond the snowline tend to form larger, gas-rich planets like Jupiter and Saturn, which can accumulate vast amounts of ice and then rapidly capture large envelopes of gas. Inside the snowline, where only rocky and metallic materials are solid, smaller, denser terrestrial planets like Earth and Mars are more likely to form. The snowline is thus a gentle cosmic divider, elegantly influencing the composition and size of planets that emerge in different parts of a star system, patiently shaping the fundamental character of newly forming worlds. Finally, the metallicity, or heavy element content, of a star significantly influences the type of planets that form around it. In astronomy, metals refer to all elements heavier than hydrogen and helium, which were the primary elements created in the Big Bang. These heavier elements, forged in the hearts of ancient stars and dispersed through the cosmos by their final bursts of radiance, are the essential building blocks for rocky planets, and also play a crucial role in the formation of giant planets. Scientists have observed a clear correlation. Stars with higher metallicity, meaning they contain a greater abundance of these heavier elements, are more likely to host large gas giant exoplanets. This is because a richer supply of these metals in the protoplanetary disk provides more solid material for planetary cores to form, which then allows them to grow massive enough to accrete large envelopes of gas. Conversely, stars with very low metallicity are less likely to host large planets. This gentle cosmic connection highlights how the chemical history of the universe and the composition of individual stars profoundly influences the types of planetary families they can cradle. It's a serene reminder that the elements woven into a star's fabric subtly dictate the potential for worlds to form around it, creating a delicate interplay between stellar composition and planetary destiny. As we gently drift further into the intricate dynamics of planetary systems, we uncover orbits that are far from the nearly circular paths familiar in our own solar system. Indeed, some exoplanets have highly eccentric, egg-shaped orbits, tracing elongated paths around their parent stars. Unlike Earth's nearly circular journey, these worlds embark on a profound celestial pendulum swing, bringing them incredibly close to their star at one point in their orbit, known as periastron, and then carrying them far away at another, called apoastron. This dramatic variation in distance results in immense fluctuations in the amount of stellar radiation received by the planet. Imagine a world experiencing scorching, brief summers as it swoops close to its sun, followed by long, frigid winters as it recedes into the distant reaches of its system. The gentle yet powerful gravitational forces at play sculpt these elongated paths, creating environments of extreme temperature swings and profound atmospheric changes. These eccentric orbits a planets can navigate their stellar neighborhoods, silently enduring vast shifts in their cosmic conditions, each journey a unique and unhurried passage through space. The elegant geometry of these paths speaks to the complex gravitational dance that shapes the destiny of distant worlds. Adding another layer of orbital complexity, planets can also orbit retrograde, meaning they gracefully move in the opposite direction of their star's spin. In our solar system, all planets orbit the Sun in the same direction that the Sun rotates, a configuration known as prograde. This is a natural outcome of formation from a rotating protoplanetary disk. However, the discovery of exoplanets with retrograde orbits presented a serene puzzle to astronomers. This unexpected alignment suggests that powerful gravitational interactions must have occurred in the early history of these systems. Perhaps a close encounter with another massive planet or a passing star gently nudged the planet into a reversed orbit. Alternatively, the star itself might have flipped its rotational axis, or the protoplanetary disk could have been significantly warped by external forces. These retrograde worlds are a quiet illustration of the dynamic and sometimes chaotic processes that can shape a young planetary system. They remind us that the initial conditions of a star's birth can be profoundly altered over eons, leading to surprising and elegant orbital configurations that defy our initial expectations, a testament to the subtle yet persistent forces of cosmic rearrangement. The intricate gravitational dance within multi-planet systems can also lead to inherently unstable arrangements. While planets generally settle into stable orbits, the delicate balance of gravitational interactions between multiple celestial bodies can sometimes be disrupted over immense timescales. When planets are too close or their masses are not ideally distributed, The constant gravitational tugs and pulls can gradually perturb their orbits, causing them to slowly drift. Over millions or even billions of years, these subtle disturbances can accumulate, leading to significant orbital rearrangements. One planet might experience a gentle yet persistent acceleration, while another might be slowly decelerated, eventually leading to a close encounter that dramatically alters their paths. This instability is not a sudden, dramatic event, but rather a slow, patient unfolding of gravitational dynamics, a gradual resculpting of the system's architecture. These systems serve as a tranquil reminder that not all planetary homes are destined for eternal calm. Some are subject to slow, graceful reconfigurations that can profoundly change their future, a quiet testament to the ever-present, shaping hand of gravity. In the most extreme cases of such instability, planets can be gently ejected from their star system entirely, becoming the rogue planets we discussed earlier. This profound cosmic departure typically occurs when a planet experiences a particularly strong gravitational interaction with a more massive sibling planet. During a close encounter, the gravitational forces can act like a slingshot, imparting enough energy to one of the planets to send it on a solitary trajectory out of the star's gravitational embrace. This is not a violent expulsion, but rather a slow, elegant separation, as the planet gradually drifts away from its stellar family. Once ejected, these rogue planets embark on an endless, unhurried journey through the interstellar void, adrift in the vast, cold expanse between star systems. They are quiet, solitary wanderers, forever disconnected from the warmth and light of a parent star, their surfaces likely frozen and dark. Their existence as free-floating worlds is a testament to the dynamic and sometimes solitary paths that planets can take, a serene consequence of gravitational interactions in the early lives of planetary systems. The combined effects of a planet's orbital tilt and its eccentric path can lead to some planets experiencing extreme seasonal changes. While Earth enjoys relatively mild seasons due to its moderate axial tilt and nearly circular orbit, exoplanets with highly elongated orbits and significant axial tilts can experience profound and dramatic shifts in their climate. As a planet on an eccentric orbit approaches its star, it might experience a brief, intense summer, followed by a long, deep winter as it recedes. If, in addition, its rotational axis is tilted significantly relative to its orbital plane, the planet's poles could experience periods of perpetual daylight or darkness, leading to even more pronounced seasonal contrasts. Imagine a world where the amount of sunlight varies by hundreds of % over a single year, creating cycles of intense heat and profound cold. These gentle yet significant variations shape the planet's atmospheric circulation, ice caps, and even geological activity. Such worlds are silent testaments to the complex interplay of orbital mechanics and stellar illumination, where the rhythm of the seasons is magnified into a grand, unhurried cosmic drama of light and shadow, profoundly influencing the planet's long-term environmental evolution. Despite the potential for instability, certain gravitational arrangements can also lead to remarkable harmony. Orbital resonances can create stable, repeating patterns in multi-planet systems, fostering a sense of celestial order. An orbital resonance occurs when the orbital periods of two or more planets are in simple whole number ratios, such as 1 to 2 or 2 to 3. For example, if one planet completes 2 orbits in the same amount of time that a neighbor completes 1, they are in a 2 to 1 resonance. These precise relationships mean that the planets exert regular, gentle gravitational nudges on each other at the same points in their orbits, reinforcing their paths and helping to stabilize the entire system over vast stretches of time. Instead of leading to chaos, these periodic interactions can lock planets into a predictable, rhythmic dance, preventing ejections or collisions. The TRAPPIST-1 system, with its 7 planets, provides a beautiful example of such a resonant chain, where the planet's orbital periods are all linked in a harmonious, elegant sequence. These resonant systems are a tranquil illustration of cosmic order, where gravity's subtle touch orchestrates a perfectly synchronized celestial ballet, ensuring the long-term stability and serene continuity of multiple worlds. They are a quiet testament to the universe's capacity for intricate, self-regulating beauty in its grand design. Our serene exploration of exoplanets now turns to the truly unique and captivating planetary types that populate the cosmos, revealing how diverse worlds can be. Among these are the intriguing eyeball planets, a descriptive term for tidally locked worlds with a scorching hot star-facing side and a perpetually frozen dark side. Imagine a planet caught in an unwavering gravitational embrace with its parent star, so that one hemisphere is forever bathed in searing daylight, while the other remains in an eternal frigid night. On the sun-facing side, temperatures can soar to extreme levels, potentially, causing any surface liquid to boil away, leaving behind vast dry plains or even molten landscapes. Conversely, the dark side would be locked in a deep freeze, with thick ice sheets and perpetual glaciers. Between these two extremes lies a narrow, crescent-shaped zone, where conditions might be more moderate. Here, the slow transition from intense heat to profound cold could create unique atmospheric phenomena and potentially allow for liquid water to exist, either in vast, tranquil lakes or as flowing rivers at the edges of the frozen expanse. The stark contrast across an eyeball planet's surface paints a vivid picture of a world shaped by the relentless, yet elegant, forces of tidal locking, a serene duality of cosmic existence. Our ability to even conceive of such extraordinary worlds is a testament to the patient ingenuity of scientific observation, particularly through the deployment of advanced space telescopes. The Kepler Space Telescope, for instance, embarked on a groundbreaking mission that quietly transformed our understanding of planetary prevalence, discovering thousands of exoplanets using the subtle transit method. Launched in 2009, Kepler was a dedicated planet hunter, staring patiently at a single patch of sky containing over 150,000 stars. Its mission was to detect the tiny, rhythmic dips in a star's brightness that occur when an orbiting planet gracefully passes in front of it, momentarily blocking a fraction of its light. This delicate flickering, often just a fraction of a percent of the star's total luminosity, was meticulously observed over years. Kepler's tireless vigil unveiled a universe teeming with worlds, from scorching hot Jupiters to Earth-sized candidates in habitable zones. Its vast harvest of data profoundly demonstrated that planets are not rare, but rather a common, almost ubiquitous feature of our galaxy. The silent, steady gaze of Kepler opened our eyes to the astonishing diversity and sheer number of planets beyond our solar system, laying a tranquil foundation for future exoplanet exploration and revealing the quiet hum of countless hidden worlds. Its legacy is a testament to the power of sustained, patient observation in unveiling cosmic truths. Building upon Kepler's pioneering work, the Transiting Exoplanet Survey Satellite, or TESS, is currently searching for planets around bright nearby stars. Launched in 2018, TESS takes a wider, all-sky approach compared to Kepler's focused stare. It observes nearly the entire sky, section by section, over a period of 2 years, searching for those same subtle dips in stellar brightness caused by transiting planets. By focusing on stars that are relatively close to Earth and significantly brighter, TESS aims to discover exoplanets that are much easier for follow-up studies, particularly for atmospheric analysis by future, more powerful telescopes. The gentle sweep of TESS across the celestial sphere is systematically building a census of nearby planetary systems, particularly targeting smaller, potentially rocky worlds. This strategic shift allows astronomers to gather more detailed information about individual exoplanets, moving beyond mere detection to a deeper understanding of their characteristics. TESS is quietly expanding our immediate cosmic neighborhood, illuminating the presence of new worlds that are close enough for a more intimate and serene study, gradually filling in the map of planetary companions to our stellar neighbors. Its unhurried and comprehensive survey promises to reveal a wealth of new insights into the nearest exoplanetary systems. Looking further into the capabilities that allow us to unravel the secrets of these distant atmospheres, the James Webb Space Telescope, or JWST, is capable of analyzing the atmospheres of exoplanets with unprecedented detail. Launched in 2021, the JWST is a marvel of engineering, designed to observe the universe primarily in infrared light. This capability is crucial for exoplanet studies because infrared light can penetrate the hazes and clouds that might obscure visible light, and it is also where many key molecular signatures of atmospheric gases are most prominent. When an exoplanet transits its star, the JWST can capture the starlight filtered through its atmosphere with exquisite precision, allowing scientists to identify the subtle chemical fingerprints of water, methane, carbon dioxide, and potentially even biosignatures like oxygen. Its powerful mirror and sensitive instruments enable a level of spectroscopic analysis that was previously impossible, offering a profound, tranquil glimpse into the very air that envelops these distant worlds. The JWST is gently unlocking the atmospheric mysteries of exoplanets, providing us with the most intimate chemical portraits of alien skies, a silent and serene beacon in our quest for understanding other worlds. As our capabilities gently grow, future missions are being designed with even more specialized roles. For example, missions like Ariel, the atmospheric remote sensing infrared exoplanet large survey, will specialize in studying exoplanet atmospheres. Planned for launch in the mid-2020s, Ariel is dedicated to observing a large and diverse sample of exoplanets in infrared and visible light. Its primary goal is to conduct a systematic survey of hundreds of exoplanet atmospheres, creating a comprehensive catalogue of their chemical compositions and thermal structures. By focusing specifically on atmospheric characterization, Ariel will complement the broader surveys of TESS and the detailed observations of JWST, providing a statistical overview of exoplanet atmospheres across different types of planets and stellar environments. This dedicated approach will allow astronomers to build a clearer picture of how planets form and evolve, and what factors influence their atmospheric stability and potential for habitability. Ariel represents a serene, focused effort to understand the very breadth of these distant worlds, systematically unveiling the atmospheric tapestry of the galaxy, one gentle spectral signature at a time. Another eagerly anticipated future mission, Plato, the Planetary Transits and Oscillations of Stars mission, will specifically search for Earth-like planets orbiting Sun-like stars in the habitable zone. Set to launch in the mid-2020s, Plato's design features an array of multiple telescopes that will continuously monitor large areas of the sky for months or even years. Its primary objective is to find rocky planets, comparable in size to Earth, that orbit stars similar to our Sun, specifically within their respective habitable zones. Plato's extended observation periods and precise measurements will allow it to detect these small, distant worlds and characterize their sizes and orbital periods with high accuracy. The mission's goal is to identify a statistically significant sample of these potentially Earth-like planets, providing crucial data for understanding their prevalence and formation. This serene survey will help us answer fundamental questions about how common Earth-like worlds are and how they might differ from our own, gently expanding our census of truly habitable cosmic abodes. The patient, wide-field gaze of Plato represents a dedicated effort to find our potential cosmic twins, illuminating the subtle signs of life's potential cradles. And while space telescopes provide an unparalleled vantage point, ground-based telescopes using adaptive optics can also directly image some exoplanets. Adaptive optics is a sophisticated technology that compensates for the blurring effects of Earth's turbulent atmosphere in real time. By rapidly adjusting deformable mirrors, these systems can remove the atmospheric distortion, allowing ground-based telescopes to achieve much sharper images. This technique is particularly effective for directly observing large, bright exoplanets that are far from their parent stars, where the planet's light is not overwhelmed by the glare of its sun. While challenging, Direct imaging provides invaluable information about an exoplanet's appearance, brightness, and even its atmospheric composition, offering a rare, tranquil glimpse of these worlds in isolation. It is a testament to human ingenuity, finding ways to gently pierce through Earth's atmospheric veil to capture the distant glow of alien worlds, enhancing our direct visual connection to the exoplanetary realm. These gentle technological advancements allow us to extend our reach, patiently capturing the faint reflections of worlds that once seemed forever out of sight. Our journey through the cosmos now takes a serene turn towards the grand statistical insights gleaned from these discoveries, painting a broader picture of our galactic home. Statistical analysis suggests there are more planets than stars in our galaxy, a truly profound revelation. For generations, humanity gazed at the countless stars in the night sky, considering them the primary celestial bodies. Yet, the patient accumulation of exoplanet data now quietly indicates that for every luminous star, there may be at least one, and often several, planets gracefully orbiting. Our Milky Way alone contains hundreds of billions of stars, meaning the total number of planets could easily reach into the trillions. This astonishing abundance means that worlds are not a cosmic rarity, but rather an integral and pervasive component of galactic architecture. It is a tranquil thought, suggesting a universe generously populated with countless silent spheres, each a unique expression of cosmic formation, collectively forming an intricate, sprawling tapestry of matter, far exceeding the number of its stellar beacons. This quiet census of worlds reshapes our perspective, placing planets at the very heart of galactic demographics. Among this vast population, the most common type of star in the galaxy, red dwarfs, are also the most common hosts for exoplanets. These small, cool, and relatively dim stars make up approximately 3/4 of all stars in the Milky Way. Their longevity, often burning for trillions of years, far exceeds that of sun-like stars, offering immense timescales for planetary evolution. Because red dwarfs are less luminous, their habitable zones, where liquid water might exist, are located much closer to the star than in systems like our own. This close proximity means planets orbiting red dwarfs are often tidally locked, presenting one side eternally to their star. Despite the challenges, such as potential stellar flares, the sheer number of red dwarfs and their propensity to host planets makes them prime targets in the search for life. Their quiet, enduring presence suggests that the majority of life in the universe, if it exists, might very well be found under the gentle, reddish glow of these long-lived stars, patiently awaiting discovery on worlds that have known billions of years of tranquil existence. Our exploration of galactic distribution also reveals that many exoplanets have been found in the galactic bulge, the central densely packed region of the Milky Way. This bustling heart of our galaxy is a crowded metropolis of old stars, gas, and dust, a stark contrast to the quieter spiral arms where our solar system resides. The sheer density of stars in the galactic bulge means that gravitational interactions are more frequent and intense, potentially shaping planetary systems in unique ways. Despite these dynamic conditions, the abundance of stars here naturally leads to a high concentration of planets. Finding exoplanets in such a crowded environment demonstrates the resilience of planetary formation, even in regions where stellar encounters are common. It suggests that the gentle processes of accretion and orbital stability can unfold successfully amidst the galactic hustle and bustle, creating a rich array of worlds in the very core of our galaxy. The silent myriad stars of the bulge likely cradle an untold number of planets, each a small, enduring presence in the vibrant galactic center. Even more surprisingly, planets have been detected in globular clusters, which are ancient, tightly packed groupings of stars. For a long time, astronomers believed that the intense gravitational interactions between stars in these dense clusters would make it nearly impossible for planets to form or to remain in stable orbits. The constant gravitational tugs from nearby stars were thought to either prevent planetesimals from accreting or to gently eject planets from their systems. However, the patient application of advanced detection methods, particularly gravitational microlensing, has unveiled planetary candidates within these venerable stellar communities. This discovery is a testament to the universe's capacity for planetary persistence, even in environments once considered too dynamic for their stable existence. These planets, orbiting some of the oldest stars in the galaxy, offer a tranquil glimpse into the most ancient planetary systems, silently enduring for eons within the dense spherical embrace of their stellar families. Their quiet presence within these ancient stellar cities reshapes our understanding of where planets can not only form, but also patiently survive for cosmic timescales. Stepping back to consider the broader landscape of exoplanet types, the prevalence of super-Earths and mini-Neptunes indicates that our solar system is somewhat unique in its composition. As we have gently explored, these intermediate-sized planets, larger than Earth but smaller than Neptune, with or without thick atmospheres, are by far the most commonly observed types of exoplanets. Yet our own solar system contains no planets of this specific scale. We have small rocky worlds and large gas giants, but nothing in between. This absence suggests that the processes that shaped our solar system, while leading to a stable and life-supporting arrangement, were not necessarily typical. The widespread occurrence of super-Earths and mini-Neptunes elsewhere implies that the conditions and raw materials in many other protoplanetary disks frequently favor the formation of these intermediate types. This gentle realization encourages us to view our solar system not as a standard template, but as one of many possible, equally elegant outcomes in the grand cosmic lottery of planet formation. Our solar system's distinct architecture is a quiet marvel, a unique planetary fingerprint in the vast cosmic expanse. Perhaps the most exciting statistical insight for the search for life is the estimate that at least 1 in 5 sun-like stars has an Earth-sized planet in its habitable zone. This quiet yet profound statistic suggests that potentially habitable worlds are not exceedingly rare, but rather a common occurrence across the galaxy. Considering the hundreds of billions of sun-like stars in the Milky Way, this estimate translates to tens of billions of potentially Earth-sized planets residing in the life-friendly zones around their stars. While Earth-sized and habitable zone do not automatically guarantee life, they represent the fundamental prerequisites for liquid water and a rocky surface, conditions conducive to life as we know it. This gentle numerical revelation fuels the serene optimism of astronomers and astrobiologists, suggesting that the universe might be generously populated with worlds capable of nurturing life. Each of these quietly orbiting spheres holds the potential for unique biological stories, patiently unfolding over eons under the gentle gaze of their sun-like stars. This estimate transforms the search for extraterrestrial life from a distant hope into a tangible, widespread possibility, painting a tranquil and hopeful picture of a cosmos brimming with potential. The quiet promise of these countless worlds beckons us to continue our patient search, creating molten rock or vast, dry deserts. A gentle, yet persistent wind might carry heat from the day side towards the cooler night side, but the contrast remains stark. The Terminator line, a band of perpetual twilight, could host a narrow strip of more temperate conditions, perhaps even a quiet, flowing ocean where the ice meets the heat. These planets are a tranquil illustration of how extreme stellar proximity and tidal forces can sculpt dramatically different environments on a single celestial body, a serene duality of cosmic existence. Hypothetical carbon planets offer another fascinating glimpse into the universe's chemical diversity. These are theoretical worlds rich in carbon, potentially possessing diamond interiors. Unlike Earth, which is rich in oxygen and silicon, these planets would form in star systems where carbon is far more abundant than oxygen. Under immense pressure and heat, deep within such a planet's mantle, carbon could crystallize into vast, shimmering diamond layers, or even form liquid diamond oceans, as we mused earlier. Imagine a world where the very ground beneath your feet is composed of precious gems, or where mountains of graphite rise under a sky perhaps tinted by carbon-based hazes. These planets would challenge our silicate-dominated understanding of geology, offering a tranquil vision of worlds forged from a different chemical palette. Their existence would be a testament to the myriad ways elements can combine and transform under cosmic forces, creating serene and unexpected forms of planetary beauty, each a silent jewel in the galactic crown. In orbits even closer to their fiery stars, we find lava planets, which are terrestrial worlds so close to their suns that their surfaces are perpetually molten. These infernal worlds are essentially oceans of glowing, liquid rock, constantly churned by tidal forces and volcanic activity. The intense stellar radiation keeps their surfaces at temperatures high enough to melt silicates, creating a dynamic, incandescent landscape. Imagine a world where volcanoes erupt ceaselessly, feeding vast, slow-moving rivers and lakes of molten rock, reflecting the harsh glare of its parent star. The sky above might be thick with vaporized rock and metallic gases, creating a hazy, oppressive atmosphere. These planets offer a dramatic yet strangely calm illustration of extreme planetary environments to reshape a world's very crust. They are a silent, fiery testament to the universe's capacity for elemental transformation, where the solid ground we know on Earth gives way to a gently glowing, fluid surface, a mesmerizing display of cosmic heat. Moving to the outer reaches of many exoplanetary systems, we often encounter ice giants like Neptune and Uranus, which are common exoplanet types composed largely of volatiles. These distant worlds are significantly larger than Earth, but smaller than gas giants like Jupiter, characterized by their deep atmospheres of hydrogen, helium, and methane, surrounding icy mantles of water, ammonia, and methane. They formed in the cold outer regions of their systems, beyond the snow line, where these volatile compounds could condense into solid ice. Their serene, deep blue or teal hues, caused by methane-absorbing red light, paint a picture of tranquil, frigid giants. Their immense size and cold temperatures mean they likely possess powerful internal heat sources, driving complex atmospheric dynamics and potentially harboring vast, deep oceans of liquid volatiles beneath their gaseous envelopes. These majestic icy spheres are a testament to the abundance of water and other volatiles in the outer reaches of protoplanetary disks, quietly filling the cosmic landscape with their serene, ethereal presence. Between the gas giants and the terrestrial worlds lie gas dwarfs, which are smaller than Neptune but still possess thick, hydrogen-rich atmospheres. These planets represent another common type of exoplanet not found in our solar system. They are typically larger than super-Earths, but smaller than mini-Neptunes, characterized by their relatively low density due to their substantial gaseous envelopes. Scientists believe that these planets formed with a significant amount of hydrogen and helium gas, but did not grow massive enough to become full-fledged gas giants like Jupiter. Their atmospheres are likely deep and opaque, making it challenging to study their solid or liquid cores. The existence of gas dwarfs further underscores the wide spectrum of planetary compositions and sizes in the universe, highlighting the diverse outcomes of planet formation. These small, atmospheric worlds drift through space, their thick gaseous shrouds gently concealing their inner nature, a serene reminder of the subtle variations in planetary evolution. Finally, the concept of desert planets suggests that worlds could be habitable even outside the traditional habitable zone if they have enough water to sustain humidity. This intriguing idea challenges the strict boundaries of the Goldilocks zone. A planet with a very small amount of water, perhaps just enough to create a thin, humid atmosphere, could potentially retain that water in its atmosphere, even if its surface is largely dry and hot. This atmospheric humidity could act as a greenhouse gas, warming the planet and allowing for localized pockets of liquid water, such as underground reservoirs or polar ice caps, to persist. Imagine a world where vast deserts dominate, but a persistent, subtle atmospheric moisture creates a gentle, habitable microclimate. Such a planet might be tidally locked, with the most temperate conditions found along the Terminator line, where the atmospheric circulation could transport enough moisture to sustain life. These desert worlds' habitability is not solely dependent on a planet being entirely covered in liquid water, but can also arise from a delicate balance of atmospheric conditions, patiently nurturing life in unexpected, arid cosmic locales. These varied planetary types, from scorching eyeball planets to frigid ice giants, and from molten lava worlds to potentially humid desert spheres, underscore the universe's boundless creativity in crafting celestial bodies. Each discovery gently expands our cosmic imagination, revealing new possibilities for the forms that worlds can take and the conditions under which they exist. The patient study of these unique exoplanets not only enriches our understanding of planetary science, but also invites us to contemplate the sheer artistry of cosmic evolution, where gravity and chemistry conspire to produce an endless gallery of serene and diverse worlds. It is a quiet celebration of the universe's boundless forms, each planet a testament to nature's elegant design. To uncover these distant wonders, astronomers rely on a suite of sophisticated tools and dedicated missions. To our own, our patient search for distant worlds naturally extends beyond planets themselves to their celestial companions. The existence of exomoons, which are moons orbiting exoplanets, is not only theoretically possible, but also actively searched for by astronomers. Just as our own gas giants host entire families of diverse moons, it is highly probable that many of the exoplanets we discover are also accompanied by their own natural satellites. These exomoons, if they exist, would add another layer of complexity and potential habitability to distant planetary systems, creating even more diverse environments for life to perhaps gently emerge and flourish. The quiet prospect of discovering these orbiting companions represents a profound next step in our cosmic exploration. Indeed, the concept of tidal heating from a large exoplanet could make an exomoon habitable, similar to Jupiter's moon Europa in our own solar system. Europa, a moon of Jupiter, experiences internal heating due to the gravitational tug-of-war with its massive parent planet. This gentle kneading generates enough warmth to keep a vast subsurface ocean of liquid water from freezing, despite its great distance from the Sun. Similarly, an exomoon orbiting a large gas giant exoplanet could experience strong tidal forces, creating enough internal heat to maintain liquid water beneath an icy crust, or even support active geology. This internal warmth could provide a stable energy source for life, independent of the parent star's radiation, creating a serene, hidden refuge. Such a tidally heated exomoon would offer a unique pathway to habitability, a tranquil oasis of liquid water gently warmed by the gravitational embrace of its giant companion, patiently nurturing any life that might arise within its depths. This leads to the fascinating idea of hypothetical Goldilocks moons, which could orbit gas giants that themselves reside within the habitable zone of their star. Imagine a colossal gas giant, a distant cousin of Jupiter, gracefully orbiting its sun at just the right distance for liquid water to exist on the surface of any accompanying rocky moon. This combination offers a dual layer of potential habitability. The moon receives gentle warmth from its star, and it could also benefit from the internal tidal heating provided by its enormous parent planet. Such a Goldilocks moon might experience a more stable climate than a planet directly orbiting the star, protected by its giant companion's magnetic field and enjoying a more consistent energy input. These moons represent a serene, double-layered possibility for life, combining both stellar warmth and planetary tidal energy to create potentially thriving environments. The quiet contemplation of such worlds expands our understanding of where life might find a gentle home in the vastness of space. Detecting an exomoon, though incredibly challenging, would be a significant step in the search for extraterrestrial life. The signals from exomoons are expected to be extremely faint, requiring even more sensitive instruments and sophisticated detection techniques than those used for exoplanets. Scientists are actively developing methods to spot these elusive companions, looking for subtle variations in the transit-like curve of an exoplanet or tiny wobbles in its radial velocity. A confirmed exomoon discovery would not only add a new dimension to our understanding of planetary system formation, but would also open up entirely new avenues in astrobiology. It would confirm that the complex hierarchies of celestial bodies are common throughout the cosmos, adding new dimensions to our cosmic family portrait. Adding to the majestic visual diversity of these distant worlds, some exoplanets may possess extensive ring systems, much larger than Saturn's. Imagine a gas giant, hundreds of light years away, adorned with a breathtaking array of rings, perhaps hundreds of thousands of miles wide, spanning a vast expanse of its stellar system. These rings, composed of countless icy and rocky particles, would reflect the starlight with a serene brilliance, creating a luminous halo around the planet. Such a colossal ring system would dramatically alter the appearance of the exoplanet in its sky, casting immense, slowly moving shadows across its surface and any accompanying moons. The gravitational forces required to maintain such expansive and intricate structures speak to the delicate balance of accretion and disruption within planetary systems. These grand ringed worlds are a tranquil testament to the universe's capacity for creating celestial artistry on an awe-inspiring scale, silently circling their stars as magnificent, sculpted jewels. However, the delicate dance of celestial mechanics also presents profound challenges. The stability of exomoon orbits is a complex area of study for astronomers. Just as planets must maintain stable paths around their stars, moons must navigate the intricate gravitational fields of both their parent exoplanet and the distant host star. This dual gravitational influence creates a dynamic and often precarious environment. An exomoon's orbit must be sufficiently close to its planet to avoid being pulled away by the star, yet not so close that it risks being tidally ripped apart by its massive companion. Furthermore, the presence of other planets in the system can introduce additional gravitational perturbations, potentially destabilizing exomoon orbits over billions of years. Scientists meticulously model these complex interactions to predict which exomoons could maintain long-term stability, identifying the quiet cosmic sweet spots where these potential satellites might gracefully endure. This intricate gravitational ballet underscores the delicate balance required for celestial structures to persist, a serene testament to the nuanced forces that sculpt the architecture of distant planetary families. As we continue our exploration of the extraordinary phenomena found on exoplanets, we observe worlds undergoing profound transformations. Some exoplanets are, in essence, evaporating, gently losing their atmospheres to the relentless radiation of their host stars. This slow, unhurried process primarily affects planets that orbit extremely close to their suns, particularly those subjected to intense ultraviolet and X-ray radiation. The high-energy light from the star heats the upper layers of the planet's atmosphere to such extreme temperatures that the gas molecules gain enough energy to overcome the planet's gravitational pull, gradually drifting away into space. This atmospheric escape can be a significant factor in the evolution of exoplanets, transforming gas giants into dense, barren cores over billions of years. Imagine a planet slowly shedding its gaseous shroud, its essence gently dissipating into the vast cosmic void. This quiet erosion, sculpting force of stellar radiation, patiently reshaping worlds and influencing their long-term potential for habitability. The silent, ethereal plumes of escaping gas paint a picture of a planet in a state of continuous, unhurried transformation. Adding to this atmospheric drama, stellar flares from active stars can also strip away exoplanet atmospheres, especially for planets orbiting close to red dwarfs. Red dwarfs, though smaller and cooler than our Sun, are often more magnetically active, prone to unleashing powerful, sudden bursts of energy in the form of flares. These stellar outbursts eject streams of highly energetic particles and radiation, that can bombard any nearby planets. For worlds orbiting within the habitable zone of an active red dwarf, these frequent flares can be a significant threat, eroding their protective atmospheric layers over vast timescales. While a planet's magnetic field can offer some defense, a persistent barrage of intense flares can still lead to substantial atmospheric loss. This gentle, yet potent, stellar activity highlights the delicate balance of forces governing a planet's ability to retain its atmospheric envelope. It reminds us that the quest for life must consider not only a star's average output, but also its periods of heightened activity, which can subtly, yet profoundly, influence the long-term evolution of its planetary companions. In a cosmic dance of protection, strong magnetic fields on exoplanets could potentially shield their atmospheres from the erosive effects of stellar winds and flares. Just as Earth's magnetic field, generated by its molten core, deflects harmful solar particles, a similar protective bubble could exist around distant worlds. A robust magnetosphere would act as a gentle barrier, diverting the energetic streams of charged particles emanating from a star, preventing them from directly impacting and stripping away the planet's atmosphere. Without such protection, a planet's atmosphere could be slowly, yet relentlessly, eroded over billions of years, rendering it barren and exposed. The presence of a strong magnetic field is therefore considered a crucial factor for a planet's long-term habitability, especially for worlds orbiting active stars or those in very close proximity to their sun. This invisible yet powerful shield represents a serene guardian, quietly safeguarding the delicate atmospheric layers that might harbor life, a testament to the profound interplay between a planet's interior dynamics and its external cosmic environment. Turning our attention to atmospheric circulation, super-rotating atmospheres, much like the one observed on Venus in our own solar system, might be common on tidally locked exoplanets. On a tidally locked world, one side perpetually faces its star, creating an intensely heated day side, while the other remains in eternal night side cold. This extreme temperature difference drives powerful atmospheric currents. Imagine a vast, unhurried flow of atmosphere that moves much faster than the planet's rotation, effectively transporting heat from the scorching day side towards the frigid night side. This super-rotation creates a more uniform temperature distribution across the planet than might otherwise be expected, helping to circulate heat and potentially moderate extreme conditions. The gentle, yet persistent, atmospheric currents would create a dynamic and complex weather system, a serene ballet of global winds perpetually striving to balance the planet's thermal extremes. This phenomenon offers insights into how atmospheres on tidally locked worlds might regulate their climates, patiently striving for equilibrium in the face of profound stellar influences. On these tidally locked planets, the Terminator line is a particularly fascinating region, a perpetual band of twilight where day softly meets night. This narrow permanent boundary is neither scorching hot nor freezing cold, but rather experiences an eternal dawn or dusk. Imagine a landscape where the sun always hovers on the horizon, casting long, unchanging shadows. This zone of perpetual twilight could offer the most temperate and stable conditions on tidally locked worlds, potentially allowing for liquid water to exist in a tranquil, flowing state. The atmospheric circulation might transport enough heat and moisture to this region to create a more hospitable environment, a gentle ribbon of potential habitability wrapped around the planet's circumference. The Terminator line represents a unique and serene niche for life, a stable sanctuary where the extremes of stellar illumination are gently moderated, offering a quiet, enduring promise for the emergence of unique ecosystems adapted to eternal twilight. It is a subtle, yet profound gradient of light and shadow, inviting contemplation of life's boundless adaptability. Beyond atmospheric and orbital dynamics, exoplanets can also experience profound internal activity. Indeed, exoplanets can experience volcanic activity, similar to Earth or Jupiter's intensely active moon Io. This geological dynamism is driven by internal heat, generated either by radioactive decay within the planet's core, as on Earth, or by powerful tidal forces from a massive parent planet or nearby star, as is the case for Io. Tidal forces can gently knead a moon or planet, generating immense internal friction and heat, which then melts rock and drives magma to the surface. On an exoplanet, vigorous volcanic eruptions could reshape landscapes, release gases into the atmosphere, and potentially create localized pockets of warmth and chemical energy. This internal geological activity is a serene yet powerful force of planetary transformation, constantly resurfacing worlds and contributing to their atmospheric composition over billions of years. The silent, unhurried flow of molten rock on a distant world speaks to the enduring geological processes that shape celestial bodies, creating dynamic and ever-changing planetary canvases. As our understanding of these incredible planetary phenomena deepens, the future of exoplanet research promises even more profound insights, guided by innovative technologies and ambitious new missions. Artificial intelligence and machine learning are increasingly used to sift through the vast and complex datasets gathered from exoplanet observations. The sheer volume of data, from subtle stellar dips to intricate spectral measurements, is far too immense for human analysis alone. AI algorithms can patiently and efficiently identify faint planetary signals, distinguish true exoplanets from astrophysical noise, and even categorize planetary types based on their characteristics. These intelligent systems learn from existing data, becoming ever more adept at spotting the quiet clues of distant worlds, accelerating the pace of discovery. This gentle integration of advanced computing allows astronomers to unlock more secrets from the cosmic tapestry, enabling a more rapid and comprehensive understanding of the exoplanet population. It is a serene partnership between human ingenuity and computational power, patiently sifting through the universe's whispers to reveal its hidden truths. Looking ahead, future telescopes will aim for direct imaging and spectroscopy of smaller, potentially habitable worlds. While current direct imaging is mostly limited to large, distant exoplanets, the next generation of observatories is being designed with unprecedented sensitivity and resolution. Imagine powerful new space-based instruments capable of gently blocking out the blinding glare of a distant star, allowing us to directly capture the faint light from an Earth-sized planet orbiting within its habitable zone. With this direct light, scientists could then perform detailed spectroscopy, analyzing the atmospheric composition of these smaller worlds for biosignatures like oxygen and methane with exquisite precision. This ambitious goal represents a profound leap in our capabilities, moving from indirect detection to a more intimate, tranquil observation of potentially life-bearing worlds. It is a serene vision of future discovery, patiently striving to paint clearer portraits of our cosmic neighbors, and perhaps even glimpse the colors of alien skies. The ongoing quest for exoplanets also includes the subtle yet profound search for technosignatures, which are signs of advanced technology. While the primary focus remains on biosignatures, astronomers also consider the possibility of detecting evidence of intelligent civilizations. This could include searching for artificial atmospheric pollutants, unusual energy emissions, or even organized patterns of light that might indicate mega-engineering projects, such as Dyson spheres. This gentle expansion of the search criteria acknowledges the vast potential for life to evolve into technologically advanced forms. The search for technosignatures is a quiet, patient endeavor, listening for any deliberate or incidental signals that might emanate from a distant, intelligent civilization. It represents a profound shift in our cosmic aspirations, moving beyond the detection of simple life to a serene, yet hopeful, search for cosmic companionship, patiently scanning the vastness for any echo of advanced minds. Beyond individual discoveries, understanding exoplanet demographics helps refine theories of planet formation. By observing the sheer variety of planetary systems, from hot Jupiters to super-Earths, and from multi-star systems to rogue planets, astronomers gather crucial data that challenges and strengthens existing models of how planets coalesce and evolve. The prevalence of certain types of planets, the distribution of their sizes and orbits, and the characteristics of their host stars all provide vital clues. This patient, statistical approach allows scientists to construct more accurate and comprehensive theories, gracefully explaining the diverse planetary architectures observed across the galaxy. It is a tranquil process of cosmic forensics, piecing together the formation stories of countless worlds to understand the fundamental laws that govern their birth and development, continually refining our understanding of the universe's creative processes. Our place in the cosmos also gains new context from this research. The cosmic address of our solar system within the Milky Way is increasingly relevant to the search for other life. Our solar system resides in the Orion Arm, a relatively quiet region far from the chaotic galactic center. This serene location, away from the intense radiation and frequent stellar encounters of the galactic bulge, may have provided a more stable environment for life to evolve over billions of years. Understanding the characteristics of our galactic neighborhood, such as star density, metallicity, and exposure to cosmic rays, helps scientists identify analogous regions in other galaxies or within our own that might be particularly conducive to life. This gentle self-reflection allows us to place Earth's unique circumstances into a broader cosmic context, understanding the subtle factors that contribute to its long-term habitability. It is a quiet quest for cosmic self-awareness, mapping our home within the vast, intricate tapestry of the galaxy. The next generation of telescopes will undoubtedly push the boundaries of exoplanet characterization even further. Instruments like the proposed Habitable Worlds Observatory, currently in conceptual design, aim to directly image and spectroscopically analyze Earth-sized planets in the habitable zones of nearby stars. These monumental observatories will be equipped with advanced coronagraphs to block starlight and ultra-sensitive detectors to capture the faint light from distant worlds. Imagine the possibility of not just detecting, but truly characterizing the atmospheres of dozens of potentially habitable exoplanets, searching for biosignatures with unprecedented detail. These future tools represent a serene, ambitious leap in our observational capabilities, patiently designed to provide us with the clearest, most intimate portraits of alien worlds. They promise to transform our understanding of life's potential, gently bringing us closer to answering humanity's most profound questions about our place in the universe. Ultimately, studying exoplanets helps us understand the uniqueness and commonality of our own solar system. Each new discovery, whether of a scorching hot Jupiter or a serene Goldilocks moon, provides a valuable point of comparison for Earth and its planetary siblings. By observing the vast diversity of planetary architectures and environments across the galaxy, we gain a deeper appreciation for the specific conditions that allowed life to flourish on our homeworld. We can identify which features of our solar system are common and which are rare, refining our understanding of planetary evolution. This gentle comparative study offers a profound perspective, revealing that while our solar system is a stable and life-sustaining haven, it is also just one of countless elegant arrangements in the cosmic tapestry. It is a tranquil exercise in cosmic perspective, patiently revealing the subtle balance of uniqueness and typicality that defines our home among the stars. And now, as our journey through the countless wonders of exoplanets gently draws to a close, allow these vast, distant visions to softly settle in your mind. You have drifted through a galaxy teeming with hidden worlds, from the scorching embrace of lava planets to the tranquil depths of hypothetical ocean spheres, from the serene duality of eyeball worlds to the intricate dance of moons around distant giants. You have witnessed the universe's boundless creativity, its patient formation of worlds around ancient stars and dim brown dwarfs, and the profound, unhurried evolution of planetary systems. Each discovery, a testament to human ingenuity and persistent observation, adds another delicate thread to